So our speaker tonight is Tim Perry. He's the tech lead and open source champion of software. Software has been in Bristol 2 years. 2 years. Okay, so software house based in in central Bristol. And Tim is going to talk about building resilient infrastructure with CouchDB. So I think we've got about an hour, 2 minutes.
Yeah, 50 minutes or so.
Yeah. Q&A, yeah. Okay.
Cool. Great, thanks. So yes, I'm Tim Perry, I work for software, and I want to talk about the CouchDB. I don't really want to talk about CouchDB generally that much. It's very interesting, it does some cool stuff, but I want to talk quite specifically about this particular niche, resilient infrastructure in CouchDB, and a bit about how CouchDB actually solves that problem, and then a bit about why it's actually remotely useful. So some context, software. Has anybody here ever heard of software? A few, yeah. Yeah. Half of you already work for software. Cool, yeah, so we're a bespoke software development company in Bristol and North London as well. So we do bespoke development for all sorts of other companies, other projects, building things with all sorts of various tools. And I want to talk about one of these projects a little bit today. And I should note before we get too far that we are hiring, and if you're interested in that kind of thing, you should come and talk to me or Rick in the middle there afterwards. CouchDB then. So who's heard of CouchDB before this talk? A couple? Yeah, okay. Have you used CouchDB? Excellent. No corrections. So it's an Apache project. They've got this relax tagline, and they've kind of built everything on that sort of model. So it's trying to be very simple in a lot of ways. There's no schema. It's a NoSQL database, and it's schemaless. You just put in whatever you like. The whole API is HTTP and RESTful, so it's all very accessible with whatever tools you're using, and very easy to just play around with. And the core model is quite simple and clean, and there's a lot of extra features they build on top of that. For the basic stuff, is all quite simple and easy to work with. On top of that, it works basically everywhere. So it's just a simple process you can kick off with no setup on Windows and Linux and Mac, fine. But then it's also compiled for Android and iPhone, so you can run your database on your phone, which is strange. And there's a cross-compilation for JavaScript as well, for some reason. So you've got this same kind of everything just sort of works setup. And then on top of that, you gain this enormous reliability, which is what I mostly want to talk about today. In that it's very difficult to break. And you can do some quite neat stuff on top of it that still is very difficult to break. So you can really get quite a lot of cool confidence out of that. So I don't really want to talk about too much of the general bits, but we'll go through a few of them. It's a document store. So as with Mongo and other kind of things, if you use that, everything is a document, like here, so a JSON structure. Notably, there's two special keys here, the underscore ID, which is the key of your document, the name you use to look it up, an underscore rev, which is a revision. So this is a revision number that changes as you make changes and gives you a version for the document. The API is all HTTP, as I say, so this is just how you use it with curl. You make a GET request to your CouchDB / the database within the CouchDB, and then the document ID within that database. And you pull out the document you want back, and it just comes back here with an ID and a revision number and whatever contents it's got. You can also insert documents. So again, it's just HTTP. Here we make a put to the ID of the document we'd like to create. We specify that we're sending some JSON and give the actual content of the document, and then you get back a response saying that this was successful and it was created with this ID that you provided and the revision number here. So these revision numbers get generated automatically. And have two parts. The bit before the dash is just a number. It just gets incremented atomically, 1, 2, 3, 4. And the part after the dash is a pseudo-random hash, essentially, of the document itself. This is how you would create a document if you have a specific ID in mind. You can also create it and have it generate a unique ID for you by posting instead of putting and not specifying an ID. And you can also do updates to documents as well, which you do with the same put here, but you also specify a revision. And you have to say which version you're trying to update. So you've got version 4 of a document in your database, and you want to change it. You say, I'd like to change version 4 to this new one with this new content. And if in the meantime somebody has changed it and your database now has a version 5, then it's not the most up-to-date version, and that conflicts and it will reject your change. So this is an optimistic concurrency model where you say what you're trying to update, and by doing that you ensure there's nobody else making changes at the same time.
So, did you say if you try to update the old version?
If you try and update an old version, it just rejects it.
It does reject it?
Yeah, locally. So you can't have two people making changes at the same time without knowing about it. Somebody has to explicitly think about that and deal with that problem. So this is kind of...
Can you lock it, or is it just a race condition?
So there's no locking.
So it's just a race?
It's just a race. You attempt to insert the document. You attempt to update the document, and it says no, somebody else has changed it in the meantime. And then you query, see what their changes were, merge them with whatever change you wanted to make, and then you try again. So this doesn't work in a particularly high contention environment, and you'd not do that, essentially. But in other environments, it gives you a lot more freedom and flexibility, and means you don't have to think about locking, and reading can become extremely fast, because there's none of this locking infrastructure in place.
And just, what's the underlying structure of the document? Have you gone into that, or these are just simple examples?
Underlying structure in what way?
Well, if I'm thinking of a typical traditional database, you've got table structure.
Okay, so the structure of the documents themselves is just JSON, so like this. So any kind of structure you could build from JSON, you can nest objects into objects into objects here, and that would be a single document. The sets of documents then are organized into databases. So you have, on a single CouchDB, you have database A, B, C, and each of them contains a whole bunch of documents. And that's it. The cool features, though, happen when we start building on top of this. And the one that's actually somewhat unique and interesting here is the way it manages replication. So before this point, we have a document store that runs on one machine and which you can just insert stuff and remove stuff in a very simple, basic way. You've got some JSON, you save it, you load it. That's about it. At this point, you can start having multiple CouchDBs and keeping them in sync in whatever way you like. So the replication is unidirectional. You say, I have CouchDB A and CouchDB B, and I want every change I make to A to be reflected in B, and changes get pushed through one way. And you can keep two databases in sync by setting up one going both ways, which is what we actually do here. CouchDB A gets every change in CouchDB B, and CouchDB B gets every change in CouchDB A, and they just stay the same. And you can have these two databases that stay totally in sync in lockstep as you make changes in each one. And to do that, we just do this, which is the same API, essentially, as we were using on the previous slide. You create a new document in the replicator database, which is a special database for managing replication. And the document says, read from this source, CouchDB B, into the local database, DemoDB. And this is on CouchDB A, so we're pulling stuff in from CouchDB B here, and doing this continuously, so just keep me in sync. And then we also post to the other database, CouchDB B, saying read from CouchDB A and pull it into my local one here. So they both stay in sync with one another. We're going to have these two databases where if we make a change in either one, they're going to stay together and walk forwards in lockstep. And this is where things get really interesting, because this is much more reliable than you would expect from other things. Most databases will get quite upset if some of them start falling apart, and certainly like if they all fall apart and you've got individual CouchDBs totally disconnected from one another. If these weren't CouchDBs, if this is SQL Server clusters, for example, everything crumbles and you simply can't use it anymore. Whereas CouchDBs will quite happily continue as they're working, and when you bring them back together, will reliably come back and incrementally pick up from where they left off.
Is that an active process? So they're aware that they've been disconnected and they actively then sync the changes between the two?
So they're aware they're disconnected, they retry, and once it comes back, they incrementally pick up from where they were.
So they're just picking up queues. The queue of changes as opposed to actively looking and check something back to the data to make sure that they are.
Yeah, so there is a stream of changes which they read from to pull this in. I've got some more of the details later.
They push those changes rather than pull them.
So you can do replication either way. So you can do both. In general, you want to be pulling because it means when you turn the server on, it can immediately start pulling. Whereas if you're pushing stuff and the other server's down, you're not sure quite when to start pushing again because you're not the one who's down. So pulling is slightly more reliable, but they both work fine. Not reliable, performant. It's got a bunch of other features that are interesting. It does some quite cool stuff. You can build some very interesting structures on top. I'm not going to talk about any of these. Resilient infrastructure, though, is much more interesting. It is fine as a document store. It does do some cool things, but it shines when you're trying to build this kind of really reliable stuff on top. And when I say resilient, what I'm talking about is databases that work in the face of total network disconnection from every machine to every machine, intermittent power. If you're running CouchDBs on a selection of mobile phones connected by 3G in the third world, trying to stay in sync, this kind of thing. And this lets you build shared data stores that work despite all odds, no matter what happens, through small fires and floods, this kind of thing. And this may sound ridiculous, but allows us to build a lot of interesting and powerful stuff on top. I do have a bit of a demo of this, which might work. So here I've got two scripts. On this machine, I have two CouchDBs running in virtual machines. The script on the left, in an infinite loop, creates a document in CouchDB A with the current time to the nanosecond, so a unique document, and then creates a document in CouchDB B for the current time to the nanosecond, and then repeats. So we're just creating documents as quickly as we can on two different CouchDBs. The document to the right, the script to the right, attempts to screw this up by pulling the power out of the CouchDB, waiting 30 seconds and then turning it back on, and then waiting 30 seconds and then pulling the power out of the other CouchDB. I'm using Vagrant to manage virtual machines here, which is a very cool tool, but is broadly irrelevant. Essentially, it's a computer where we pull the power out and give it no time for shutdown, no warning, nothing. So, if we look at these two CouchDBs that are currently up and running, this is the web interface for CouchDB. I've got this demo database here with no documents in it. This might be slightly easier if I show you the thing. So this is CouchDB A here running, and that's apparently also CouchDB A, which is wrong. This is CouchDB B, happily running again with no documents in. So we've got these two up here. And if we look here, we can start creating documents. And just like that, I'm firing a stream of documents. This script is going through, posting to both CouchDBs and creating unique documents here. And you can see these IDs that we get given back and revision numbers. And then over here, we go break things, and we pull the power out, and half of these stop working because one of the CouchDBs is gone. If we go back here, we can see this a bit more clearly. So this is what's currently running on this machine, these two CouchDBs replicating together, and then I've got these two scripts running locally. We start making requests, posting to both of them, and these replicate together. So as we create a document in CouchDB A, it appears in CouchDB B. Replication pulls these through, and these two databases should stay totally in sync. We then pull the power out. Replication obviously is going to stop doing anything at that point because there's nobody to talk to, and half our writes then fail. And we then turn it back on, and then we pull the power out of the other one and turn it back on. And we're going to repeatedly do this for the rest of the talk. So this maybe perhaps is a pathological case. It's a little bit ridiculous. If there is somebody in your data center right now pulling the power out of your database every 2 minutes, you are in real trouble. You should probably go. But it adds some cool stuff, I think. In particular, there are quite a few organizations and environments where you do have real trouble, or where the small risk that bad things like this might happen is so dangerous that you have to be able to deal with it. If you're building medical appliances, there's very small chance that the power might fall out and you would lose all your data is disastrous. That can't happen. If you're running infrastructure, power, internet, water generally, and you're building critical services, they have to work. If you're under strict SLAs where it costs you an enormous amount of money, if you're ever down for a moment, then they have to work all the time. And there's a lot of businesses that do have to care about this kind of thing. And businesses building on unreliable infrastructure generally. If you're building with a selection of data centers around the world and you have to handle connectivity between them, you've got dependencies on these huge cables back and forth and all this infrastructure. I don't know if anybody saw the news recently, but sharks are attacking underwater cables between the continents. And having a system that is prepared to deal with that has some use. And there's certainly businesses that are taking this into account quite seriously. So Netflix, for example, have an internal service called a Chaos Monkey that walks around their live system and turns servers off to ensure that it definitely works. And this is production Netflix. And ensures that they have to think about reliability. They cannot ignore it because the actual site will go down. And that obviously costs Netflix an enormous amount of money. So this, has definite value in these kind of cases.
Can we go back to the lecture title? Is building resilient infrastructure using CouchDB? You're not suggesting that the CouchDB document store forms part of an infrastructure, are you?
I am.
But it's a software application that sits on top of some infrastructure.
It depends what you're talking about by infrastructure. Here I'm suggesting that the data stores you run your application on top of are your infrastructure.
And would it be better titled building the unreliability out of unreliable infrastructure by using CouchDB?
Sort of, yeah, I see what you're getting at. So creating reliability on top of unreliable infrastructure.
Yeah.
Sure. I'm not talking about improving the quality of your cables or making sure your power never goes off.
Okay, but yeah, by using the CouchDB product, you're dealing with unreliable infrastructure that doesn't have any good resilience in itself because it goes up and down all over the place. And you've got a document store database product that sits on top of that and copes with these things as it ought to be able to.
Yeah, exactly. This is an example of exactly that happening. So this is a software project from a year ago for a company doing, sadly anonymized, for a company selling B2B products. So they're selling to other companies this software as a service application that is essentially critical to these other companies' businesses. It is a core product their employees need to use basically all the time, every day. And they are under strict SLAs that cost them a lot of money if it fails. They have millions of paid-for users, these employees, making a lot of requests, 50,000 requests a second average. That's a lot. For comparison, Google search takes 30,000 requests a second. This is a very busy system. They run it with a lot of servers, 3,000 spread across 25 data centers, which covers every continent in the world except Antarctica. A few times over. It's also quite highly latency sensitive because these employees are using it all the time, and the occasional blip here and there is maybe okay, but if it continuously becomes half a second slower, that's totally unacceptable. And the real problem is that all of these servers, all the time, need to be able to get to user sessions for each request. When a user connects to the system, they log in, they provide us with their authentication data and a bunch of metadata about the user. And we give them a token back, just a short hash, essentially. Every subsequent request they turn up with, they just give us that hash back, that token. And we need to get the information in the session and be able to use it to decide what to do with that request. So we've got to have that information available on all 3,000 of these servers all the time to be able to do anything. To make this a bit more difficult, none of their stuff works. They've got enormous network infrastructure problems where their data centers frequently cannot connect to each other. There is usually a data center that is disconnected from all the others. They should fix this, but they don't have the money and the time to go and fix everything all at once, which is not unreasonable, or certainly not uncommon. So there's loss of connection to these data centers. At least a couple of times a year they have total power outages in data centers. I think maybe Chicago had a few in a row. Some electricians were coming in, changing the air conditioning, and in the process unplugged the wrong thing, and poof, everything goes down. This was not very good. And on top of that, their users roam continuously. They expect to be able to log in Los Angeles, get on a plane, hop out in Cape Town, and have it work immediately. And that gets exacerbated by the way they do failover. If you're using a server in Paris and the server crashes, we don't even try another server in Paris, we switch to Frankfurt because latency matters. We don't have time to test things, we go. Which means the data has to be there in Frankfurt, ready for that switch. And finally, the data centers can't talk to each other even on a good day. Everything goes through London as a central data center, essentially. And this is hub and spoke architecture. This is a terrible idea, but it is something that exists and runs a large business that makes quite a lot of money despite this. So their previous solution for this was to have every session available in every server all the time. This has some downsides, which we'll get to in a second. To actually make this work, every time you log in, we get your authentication data and your token. We send this to a central message queue, and that message queue messages every single other server. This means every time you log in, we send one message to the queue, and the queue sends 3,000 messages back out to everybody. We've also got a normal relational SQL database that they use for server startup. Since the servers need every single session available, when they come up, they don't have any of them, so they boot up and they pull in everything from the relational database while they also start listening to the message queue and getting further updates on sessions. So they kind of bootstrap themselves from there. And this database is in London, and this message queue is also in London. As I say, this has some problems. The memory usage doesn't remotely scale. They spent a lot of time building a paging solution to push stuff onto disk instead of keeping it all in memory. That took a lot of time, was quite complicated and expensive to build, and they couldn't quite push everything down there without this getting more and more complicated. Eventually they worked out that they had about 12 months, at the current rate of growth of the business, they had about 12 months before the servers simply ran out of memory and their servers crashed. Shipping more memory to 25 data centers to upgrade 3,000 servers is impractical and very expensive. So they had to try and find some other way of re-architecting this to get rid of that. On top of this, you have big problems with single points of failure. If your data center can't connect to London, nobody can log in anymore in that data center, which isn't very good. Also, you can't turn servers on anymore because they can't connect to the database to bootstrap themselves. And in general, message queue failures are catastrophic problems. If the message queue fails, nobody can log in anywhere in the world. They lose an enormous amount of money, and it's incredibly painful. So they wanted to fix this. This is the point where we came in. They had essentially 12 months left to reorganize into some better solution that would kind of solve this problem. And we went for CouchDB with this in the end. This re-architects somewhat. When somebody logs in, when somebody makes a request now, they come in with a token and we want to know what's in their session. We first look in a least recently used cache within that server. So we keep a small cache of the currently immediately active users. If they're not in there, we then look in a CouchDB in the same data center. So if you're connecting to a server in Frankfurt, we read from the Frankfurt CouchDB. And we pull information through this, and that is the usual case. If there's anything wrong with that CouchDB, you read through to the central CouchDB in London and pull out from there. And this gives us a session in basically every case, essentially. And registration works similarly. So if you log in, you send us your authentication details and a token, and we create a CouchDB document with the token as the ID, and we store it in your local CouchDB if that's available, or in the London one if it's not, and it replicates out and everywhere gets it.
So how does the local CouchDB know there's something wrong? You say if something on local, there's something wrong. How does that make something wrong?
So these are if the servers know something's wrong with the CouchDB, and they know because every time they make a request, if at any point any of their requests to the CouchDB fail, they mark it as down, another thread in the background checks every 5 minutes to see if it's come back up, and in the meantime they just route all their requests through to the other CouchDB. And then once it comes back up, they switch back.
Okay, so the server detects when you connect.
Yeah, the server just checks. If anything goes wrong in the process of its normal requests, it reroutes and then switches back. Yes, so this is all hub and spoke replication. So everything is replicating just with London, and London replicates everything back out. So you write something in Frankfurt, and it replicates to London, then it replicates back out to Paris, and that's fine.
Am I mistaken? Is there still not a single point of failure in London?
No, because if the London CouchDB goes down, you can still log into Frankfurt, have your session registered in the CouchDB in Frankfurt, and read it out from the CouchDB in Frankfurt. And all your requests continuing to go through Frankfurt will be fine. You can't fly to Cape Town. The assumption is that it's going to come back up before you get to Cape Town, essentially. It's a substantial improvement on the previous one, but total disconnectivity between the data centers means there's nothing else you can do, essentially.
So if London goes down and you're talking to Paris, and Paris goes down, you try to go to Frankfurt, but your data's not in Frankfurt because it hasn't gone via London.
If the data centers become totally disconnected for a long period of time, they can't sync until they become reconnected. No.
What is a long period of time?
Longer than it would take to go between the data centers. And in a failover case, there is certainly a risk of this, but it's an enormous improvement on what they already had, essentially. And there's not very much else you can do. You could register with every data center on startup, but that's very expensive, and with the number of users they have, the load, it would struggle.
You say latency was an issue. You normally talk to Paris because you're in Paris, and then you have to talk to Frankfurt. Does that become an issue talking that far?
Yes. So we only do that in the failover case. If your servers in Paris fail, which hopefully happens quite rarely, and in practice happens moderately rarely.
Okay, but I mean, you could be somewhere that it does fail more often. You lose the DC for some reason or other, and you have to go to somewhere a little bit further away, down a few wires. The geographic distance becomes an issue.
It's certainly painful. This isn't so much a problem with the session management as their service as a whole, and in fact with providing any distributed service that depends on latency.
Okay, so you wouldn't want a Turkey talking to Amsterdam or something like that if it's too far?
So the failovers are pre-configured, but it attempts to fail over to a very close data center, by and large. So it minimises that distance as much as it can. Any other questions while we're here?
Yeah, just on the architecture. So this is architecture you kept that hub and scope, but you could architect it to anyone from the
Yes. They haven't done that. They should do that, and they're in the process of doing that.
In general, CouchDB support that.
Yes.
And does that take a performance hit at some point? Not enormously. Replications are more efficient if you're doing them in large batches. So if you're shifting 100 things at a time, and if you've got London pulling in the changes from everywhere and pulling them out to Paris, obviously that's going to be a lot of changes in one move, whereas if Paris is pulling from everywhere, it's going to be a smaller set. So there's maybe a small difference there, but I suspect the load would distribute better as well, so there'll be upsides and downsides. And does it make a difference in that you've got a high transaction with a read transaction? Could you support a high write transaction?
So CouchDB is much better at reads than writes. You can build moderately performant writes, but in general CouchDB is not a high performance data store. It's focused on reliability and. So the replications are batched, so it will queue up some bunch of them.
But high rate writes, you start doing replication.
Yeah, the more and more writes you have, the more and more replications you have to do, whereas reads are free, essentially.
What sort of time would you expect if somebody writes to Paris for it to appear in Frankfurt?
About 3 or 4 times round trip. It's really very quick.
Right, okay. And so that 3 or 4 times round trip is to every single data center would receive that right?
So it depends, essentially.
And not stressed.
So they've honed we have honed various polling times, essentially, for the different data centers to pull back and forth between them. And the close ones particularly we've tried to speed up. And are essentially polling extremely frequently and just pulling the changes through as fast as they can.
Okay. And if somebody in Paris makes a write for Paris, will somebody in Frankfurt need that data?
No. So the writes are a login for a user at their machine, and unless there's an immediate failover just after they write, they're not going to be using Frankfurt.
So only it needs to exist in the other location for that user. Nobody else
Yes.
needs that data.
Yes. It's all per user data. Anybody else? Okay.
So you don't really need it in 3,000 places. You just need it in n+1 places.
It has, but you don't know which one they're going to use.
But you know where they are roughly.
So A, they move, and B, we fail over. So they switch instantaneously. Sometimes.
But they need to geographically move, don't they?
So not necessarily. If a server fails in Paris, they will instantaneously switch to using
they
Frankfurt.
need to go somewhere within their local cloud, sort of thing.
Hopefully, yeah.
But they won't need to go connect to Johannesburg unless they've got on a plane to go down there.
Probably, yes.
Or something terrible happening.
Yes. So if you get a few failovers happening, then God knows where you'll end up. Alternatively, if Frankfurt is just overloaded They've got a quite complicated failover system that builds on top of this for certain cases. But in general, their previous system meant their sessions were available everywhere, and there are technically cases where that can happen. They were quite keen on keeping that as a thing that it did, essentially, as a feature. So this solves most of the problem with a selection of caveats. All of a sudden there's no single point of failure. You can take the power out of basically anything individually. You can disconnect the network, and each individual data center will keep working on its own, which was the core problem before. The data centers lost connectivity a lot, and a single data center could do nothing by itself, except London. It also scales horizontally for reads very nicely, and for reliability generally. You can put 2 or 3 CouchDBs in one data center, have them replicate, and you can just read from whichever ones are available. And if one of them goes down, you've got 2 more. So that works quite nicely. And scales horizontally. Once they start building a mesh of data centers, you can start to connect between the data centers and pull through there. And critically solves their memory problems, which stopped their business collapsing, which they were quite happy with. And also configurably solves these. You can make the cache particularly smaller or larger and trade off performance versus memory as you like. If you make the cache take in basically all the sessions, you get back to their previous solution at the cost of taking down their servers, but you can also crank that down. And from a design point of view, it's quite a lot nicer. It allowed them to get rid of all the previous infrastructure they built for storing and communicating sessions and paging them to the disk and this kind of thing, and just delete all that code, and generally encapsulates reliability to a large part out of the core service. Something else handles this now, something else which is maintained by somebody else, which is very convenient, and they no longer have to worry about it so much themselves. They don't have to build as much of their own infrastructure to solve this. So that's quite cool. This isn't all perfect. We mentioned disk usage before. There's quite a lot of writes here. A few million users logging in a day creates quite a few documents. And although we can prune these as they get old, there's still quite a lot of stuff in the database here. And CouchDB generally uses quite a lot of disk, so you have to kind of watch out for that, be aware of that as a risk. And the solution essentially was to buy more disks. And since we were putting in 25 new servers for CouchDB anyway, we just bought very big disks. But it's certainly something you need to be aware of. Ops ramp up is certainly a risk because people generally are not as familiar with CouchDB, and if you're picking any of these fancy NoSQL databases, this is kind of a concern you have to be aware of. Nobody is going to be particularly aware of how to maintain, support, deploy this. And support services generally, deployment tools were relatively immature, and we ended up kind of sticking our own stuff together in a few places. And stuff like monitoring, we built our own monitoring because it doesn't exist. It's fairly easy to do because it's just HTTP. You just connect, make requests, and check that it's up, and check various stats and this kind of thing. But you do have to be prepared that there's going to be some more legwork you have to do there. But by and large, it works very nicely. I've got another interesting example for resilient infrastructure. That is going to be quite a tangent, but it'll be fun. This is Hoodie. It's a web framework. It's a developer preview, technically. It's essentially a proof of concept, really, rather than being something you might necessarily want to immediately go and use. But it's got a lot of interesting features and some quite cool underlying principles that are going to tie back nicely into this in just a minute. The kind of principles they're trying to drive with this are 2. Firstly, avoiding writing any back-end stuff, generally, with the kind of driving motivation being that back-end is almost by definition a long way from user value. You're not immediately building visible features, you're building stuff that you're later going to use to do visible features. And if you can set up a system that allows you to just write things with everything else there and available to build on, you're in a much better place to quickly actually create stuff that's going to make you some money. And they're also trying to build this in an offline first model. I don't know if people are aware of mobile first in the web dev world. Mobile first as a concept. No. So the model is, rather than designing a web application to work on desktops, browsers with big screens and everything, all fancy gizmos, you try and build the mobile version first, essentially, and focus on providing the features you can within a very constrained environment, assuming the absolute minimum required, getting a working product from there, and then scaling up when other features happen to be available to ensure you've always got a working core product. And then other stuff is added on optionally, as it were. And offline is doing the same kind of thing for connectivity. offline first. So they're trying to work on a model here where you assume your web application isn't going to have any internet. So you're using, which sounds like an oxymoron, but you're using things like app cache to provide entirely offline web applications, and a selection of stuff we'll look at in a second to make it so that your web application can happily work entirely locally and can seamlessly manage any kind of interactions when network connectivity comes back. And in the same way that you're scaling up from mobile devices to feature-filled machines, scaling up from minimal connectivity, being disconnected, to when you act to opportunistically using the network when it becomes available. This particularly has some quite cool upsides. For starters, performance tends to be quite nice. If by default you're assuming you're offline, then you're going to do all your network stuff asynchronously. You're going to keep a nice, focused, polished UI that just works seamlessly and doesn't ever wait for the network because it's normally not there. Also, it means downtime has minimal impact because you assume your server is not working. So you've got this same kind of model going through there. That means you can scale it quite nicely with a number of clients. Moving to this model forces you to push more processing onto the client side because you don't want to have to wait for a server, and moves you to a slightly different model there. Notably, all of this comes together and means that deploys become really much less concerning. You can just take the server down, redeploy a new thing, turn it back up, and hopefully, if you've done it well, your users don't even notice, which is nice. The API looks something like this. This is JavaScript. This is essentially the code for a to-do list application, which I suspect people have seen a million of. Here we say if in the add task bit you click the submit button, then get the description of the task that you're about to add and add it to the hoodie store. So you give it a type of thing you're going to add and say I'm saving a description. And this then gets saved to local storage, which is client-side storage in a browser. So this is kind of very basic usage of hoodie, but this will just work out of the box. It's a framework, you add the library, and just like that you can save things and store it there. And you can also subscribe to things to read them back out. So here we say whenever a task is added, stick an extra list item into this list of tasks that I have. And that will get notified when you click the submit button and add a task. And will also get notified if you create tasks from somewhere else, if they come in from the network, and so on. But all of this happily works locally, and you can just write this code with hoodie, and that's an application done, although it may be terrible. What you probably want beyond this point, though, is some kind of persistence. So you've got your to-do list application, you want to associate this data with a user, you want to be able to save it and log in somewhere else and see your to-do list, not just have it locally. And Hoodie makes this kind of stuff as well quite easy, which is where this gets interesting, because typically you then have to build an authentication backend and have some database to track users and a sign-in process and so on. But this is actually all the code you end up needing. When somebody clicks login, you read the username and password they've entered, you give it to Hoodie, and when it's done, you run your login successful callback. And this ties in nicely with the kind of async model of JavaScript. People have written much JavaScript that is expecting to wait for stuff and then run a callback later. And this is where it gets interesting. There's presumably something happening in the back end, and there is. And it looks like this. So the actual code you end up writing for the application is this top left square, and everything else gets put in for you by Hoodie, notably including CouchDB. What actually happens here is that whenever you make a change locally, it gets written into the Hoodie store, which saves in local storage, and then asynchronously in the background, Hoodie have implemented the CouchDB replication API in JavaScript and do replication into a CouchDB in the background. This gives them all the same benefits as replicating with CouchDB generally. So you've got this reliable sync mechanism that's going on entirely asynchronously, separately, without you having to think about it. And all of a sudden in your application you just say save this, load this, blah, blah, blah. And if the network's there, then that gets saved and persisted. And if it's not, it gets saved and persisted when it comes back. And all that sync just happens for you. And you've got this reliable infrastructure you can build on top of. Notably, building your own sync is actually quite hard. There's a lot of annoying corner cases that will come out and bite you when you start thinking about conflicts and about recovering from failures at all sorts of different stages. And they're not particularly happy with this, and they're actually moving to CouchDB, which is an implementation of CouchDB in JavaScript. They're swapping out, so that's good, does all the work for them. But you can just use this yourself. You can just write a JavaScript application entirely on the client side that writes into a CouchDB, which replicates in the background. And all of your users can essentially have their own CouchDB in their browser that can be providing the same kind of infrastructure we're talking about for this huge B2B service. With many, many interconnected mesh network of CouchDBs but running locally to themselves. So no matter what's happening, they've got their CouchDB right there, and their data still works through that, and replication happens separately without you having to think about it. So that's quite cool. It might be surprising that some of this works, particularly the bit where we pull the power out every 2 minutes. So it's worth looking at actually some of the reasons behind it, and as it may be obvious, replication is one of the particularly cool ones. The reason replication works, and this is what we were touching on earlier, is this changes feed. You can try and read from underscore changes, and it will give you the changes since a certain point. Every database has a sequence number, which gets updated every time something changes in the database. It's essentially a version of the database. And you can query for the changes since a certain point. So you can say, give me every change since version 1, since version 4, and so on. And this is the simple way of using that API. It gives you back a list of results for each sequence number. This document changed, and this revision was added. Notably, we don't get the whole document. Typically, in a document store, your documents are quite big. You store big chunks of stuff. But we just get the revisions, so we've just got a list of what changes have happened that we can then separately read for. There's a bulk read API to make that quick. And then it tells us the last sequence number, and then we can query from that one next time. Noticeably, this is the default API for this. There's also a long polling one, where you say, I'd like to wait until there have been 100 changes and then give me them, and it will just keep this HTTP connection open and then stream them all through to you. And there's a continuous one where you just wait and it continually sends you updates of every change, and you're essentially subscribing to an entire database, and it pushes things through to you. So that's quite cool. And this is what replication builds on top of. So they've actually built a spec from this, which is up on replication.io. And there's a bunch of other tools now that are starting to become replication compatible with CouchDB, implementing the same spec. So you've got these source and target databases. You write into the target database a document that says what sequence number you've read up to, starting with 0. You then get the list of all the revisions you're missing by reading from this changes feed from the source database. For each of those revisions that you don't already have, you then go and load the documents and write them into the target, and then you update the sequence number saying I've got every change up to number 400. And then you go around again and you say give me the changes since 400, and you pull in the documents and you repeat.
And what happens when that goes wrong?
So we restart, essentially, except we don't rewrite the sequence number to 0, perhaps, obviously. Notably, step 3 makes this very reasonably efficient if it goes wrong, because we read a list of revisions, we then start loading and writing documents, and we don't update the sequence number until the end. If we're reading 1,000 revisions, and we read and write 500 of the documents into them, and it then dies, our revision number is still 1,000 back. We go and get all the, our sequence number is still 1,000 back. We go and get all the 1,000 revisions we're missing, but 500 of them are already written. So we don't have to load those, we don't have to write them again. We just load the next bunch of revisions, the next 500, write them, so we're always halfway through, and then we update the sequence number. And similarly, on a larger scale, if it fails and you've got up to sequence number 1,000, you're never going to have to load the previous 1,000. You've already got them, and the replication process already knows you've got them, so you don't have to check that. You don't have to hash the database, check some of your data in any way. You just pick up from where you left off.
And one of them goes missing?
They don't go missing, for reasons I will get to in a second. So if you actually lose all the data, it will restart replication from scratch, but it's extremely difficult to do that, for reasons I will get to in a sec. On top of that, if this fails at any point, before resuming, it waits very briefly. It waits a quarter of a second, then half a second, second, a second. So it's exponential back off up until you get to about 5 minutes, and then it just checks. Exactly 5 minutes, and then it just checks every 5 minutes, and then resumes and goes nice and fast as soon as it's back up. So we loop through here, and this gives you a system where you have these two databases that are going to stay in sync even if things break, and when things break and they come back, it will pick up where it left off and very quickly get back to where it was, and we'll hopefully see that in a minute. So this begs the question, or replication generally kind of begs the question, what happens if you get conflicting updates in disconnected databases, which is a tricky problem. CouchDB solves this with these revision numbers and multi-version concurrency control. So we have many versions of the documents, and we then decide which version we're eventually going to use. Essentially what happens is that your CouchDBs attempt to replicate realise that they've got conflicting revision numbers, and you do this by keeping the previous revision to the document so you can compare and tell where this tree of document has gone, and then arbitrarily pick one, which sounds dangerous. There is an API to go through and query for the conflicted documents and resolve conflicts yourself, but by default CouchDB will find 2 conflicts and be like, I'm using this one. It does so deterministically, so if you resolve the same conflict on totally separate databases, you will get the same answer every time, which is nice, and you're always going to end up with a consistent model of the database, even in totally isolated environments, which again is nice. But this is focusing on a model where you end up with something that definitely works, as opposed to forcing you to resolve the conflicts, which is what React does as an alternative by default, certainly. So it's focusing on a system where you've got some data that definitely works, and you can go forwards from that point. The other part that makes this reliable and make this work.
What happens to the user who wrote their data that's now being lost?
So because this is happening asynchronously, they can't get informed. The connection might come back a month later, at which point I don't know how we would talk to them. There is an API where you can go and query and say, give me all the conflicts that happened since this sequence number. So you can go in and you can have something that checks for conflicts and goes through and resolves them. So the classic example is if you if you try and read the total amount in a bank account and then increase it by 10, so you read 1,000 and then you try and write 1,010. And if somebody else has updated it to 1,010 as well, you don't end up with 2 increments. But you'd have a background process that goes through, checks if any of the bank accounts were conflicted, and then combines the 2 updates and just adds the amount together. And if you run that, say, every minute, your account numbers might get slightly out of date, but not particularly. And hopefully your bank account services are not disconnected from one another, because that sounds like a bad idea.
Will the bank use it?
Probably not. So this is what CouchDB is what you want to build on if you want reliability and availability above all else. You want it to always be accessible, and you want to be able to get at the data no matter what the cost. Whereas banks do not want to be able to get at the data no matter what the cost. If they're going to get the wrong answer and lose money, they do not want to read the data, they want to give up.
So I presume the bank is accuracy is
Yeah, consistency is generally what you want to go for. Every database needs to be able to be saying the same answer all the time. So append only B+ trees are what make sure you don't end up losing data when things go horribly wrong. A bit of a recap for anybody who doesn't remember B+ trees and didn't revise for this talk. It looks like this. So a B+ tree is essentially a binary tree where each node, rather than being a single value, is many values, here up to 4, but typically in reality hundreds. So these nodes are very wide, and this tree doesn't get very deep. You're typically going to get to 3 or 4 levels deep, even when you've got millions of things in your database. And this is how indexes work in basically every database you'll ever use. So this is what's happening in the background. This lets you critically find information within this index very quickly, as well as being able to insert information into it very quickly, which is a surprisingly difficult problem to solve. So in terms of what this actual structure means, we've got a pointer into the top of your B+ tree. So if we say we're looking for the key 3, and we want to go and find the document with ID 3, we go in, we binary search the top one, which only contains 1 value, so that's very easy. 4 is less than 4, so we take the left pointer, and if it's greater than or equal, we would take the right pointer. So we take the left pointer, we follow it down, and then we binary search this node. So is 3 less than 2? No, it's not. So we go right, is 3 3? Yes, it is. So we follow the node from the leaf at the bottom, and this takes us to the actual document. And you follow this through, and this lets you search a tree and very quickly find information in a nice structured way that is relatively manageable. If you want to insert things into this, you search it, and when you find the key isn't present, you add it, and that's about it. So we add 6, we add 7, this is very easy. If you want to add 8 now, obviously it becomes more difficult. What you essentially do is add 8 and then split the node in half and pull the middle value up, like this. So you pull the 6 up. And now if it's less than 4, if it's less than 6 and greater than or equal to 4, we follow that middle pointer, but otherwise we go to the other node, and you continue to search by doing this. And splitting like this keeps the tree balanced and keeps it efficient for searching. And the tree only ever gains height if the root actually splits, and at that point stuff falls on top.
Is that more efficient than the binary tree? The binary tree you get to go on.
So the complexity, I think, is essentially the same. They're both logarithmic. The trick is that because it's much wider, it caches enormously better. Critically, because it's much wider, it stays much shallower, which means all of the top layers, everything except the leaf nodes, stay in memory and hopefully in like L2, L3 cache in your processor. So they're extremely quickly available. And when you're a database making a lot of queries to different data all over the place, that means you read all the top bit of the index entirely, very quickly, like out of processor cache, and then you just have to make a single disk request for the last bit and pull the data out.
It's more efficient based on memory architecture rather than algorithm.
Yes, if you're doing it purely like theoretically computational complexity, they're both logarithmic, and I think with similar coefficients. But yeah. What this looks like on disk or memory is slightly interesting. So the bottom bit here, we've got these 3 nodes. Everything is just contiguous in memory. We've got pointers and then pointers between them, and then again these leaf pointers out to the data, which we'll ignore for now, but is somewhere else. When you insert something, you just change this structure. You just update a bit of it. You update a bit of it. And when you want to add the other leaf node, because we're splitting this node, you update it again. And this is where the danger comes in pulling the power out of most databases, and in fact, most processors generally. When you're updating stuff on disk, if you suddenly stop halfway through, then you end up with bizarre and corrupt data structures that don't make any sense. If you pull the power out of SQL Server, typically it will corrupt itself. You'll have to reboot it and wait for it to go through and recover everything and work out what's happened. And then hopefully go forwards, and in the meantime it will loudly complain. Whereas for reasons we'll get to in a minute, CouchDB won't do that. So as an example, we have to update 6 in the root of this tree here, and also add this leaf node, and also pull 6 and 7 out of this yellow bit here. And if we've pulled 6 and 7 out, and we've written the leaf node, but we haven't updated the top of here, then all of a sudden you've just lost these 2 values from your database. Alternatively, if you write 6 first, and you haven't written a new leaf, you've now got a pointer that just doesn't really go anywhere, and everything's a bit broken. And you can get yourself into some messy states. And this is a relatively simplistic case. Databases are very complicated. There's a lot more going on. It gets much worse. CouchDB instead is immutable, essentially, on disk. It is append only. You start with the same kind of thing, except we have to think a little bit more about the root and how this starts. And anytime you want to change a node, you just rewrite a new one. And then you follow the pointers back up, and you rewrite any ones you needed to change. So if we want to add 6, we do this. The other nodes still exist in memory and on disk for now. But we've got this new structure here that we can read from, and if we again start from the purple node and read through, we now get the new consistent model of the tree. Notably, this works completely locklessly with concurrent readers. If somebody is in the middle of reading through the other tree, their tree is still there, the tree is still valid, it's fine. They might be slightly out of date, but everything just still works, which is cool. If we write 7, we then do the same thing, and if we write new nodes, we then do the same thing. Notably, we're still reusing this node in the left because it's still valid. It doesn't have to change in any way. And in a real database, these are extremely wide. There's far more nodes here. There's a lot more going on. We only end up actually changing a node for each level. So 3 or 4 nodes out of the hundreds of thousands there are going to be flying around. On disk is where this gets very interesting and very complicated. So this is what we start with. If you're trying to work out how your tree works in CouchDB, you read from the end of the file, and this is where the magic happens. So we go to the end, we find this footer, this purple node, and it says, here's the tree over here, and then we start reading from the green one, and we follow the pointers. This is the same structure we were looking at a second ago, but flatter. So we can follow this through. Every time we want to create these new nodes, we stick them on the end, and then we put on a new footer. So as before, this means concurrent readers following through are still happily working forwards. But also means we can just start, we just read from the end and we get this new file. And critically and really interestingly means that any prefix of a CouchDB database every prefix of a CouchDB database is another valid CouchDB database. You can delete any chunk off the end and it's still a CouchDB database. And it's still totally valid and it's just a slightly older version. As long as you don't go back before the first footer, but that's a long way back. So if in fact you fail reading, because you're not doing any updates to the stuff that was already there, you never lose anything. Stuff keeps working regardless of how you break it, how you change it, how you move forward. You've got this reliable structure that is there on disk. It doesn't change and just works. This might sound reasonably inefficient, and it certainly looks inefficient once you start writing more and more of them. But there's actually a whole load of optimizations you can pull on because of this kind of thing. So these empty spaces in these leaves, for example, conceptually need to exist because that's how B+ trees work. But given that you never change the database, you don't need to actually put them on disk. You can collapse all of this down. On top of that, because you're always writing at the end of the file in a continuous batch, your writes become very efficient. You can quickly just write a single stream of data and you're done. And that's what CouchDB does. And on top of this, the disk usage doesn't get quite as bad as this looks, although this is moderately expensive for disk usage. There's actually a compaction engine that goes through in the background and removes old bits of the tree and compresses things together, essentially by copying out the live bits of the tree somewhere else and atomically switching once that's done and pulling changes as it goes. All of this means writes become a little more expensive than they are in a typical database and a little more complicated, but means reads are really easy. You don't have to think about what other people are doing, even other people writing, other people reading. You just follow the pointers and they're always valid because they're always valid. They're not going anywhere. They're not going to change. You can just follow it straight through.
Why do you say writes more expensive?
So because you have to change more of the tree, you always have to change a bunch of nodes as opposed to just updating a single bit.
Oh, right, okay, because of the quantity you're writing.
Yes, there's just more data changing.
As a stream right on the end as a single block, rather than bits and having to seek for them and things like that.
So the disk part is cheaper there, but I'm mostly talking about in-memory writes. By default, CouchDB does delayed commits, essentially, so you write out to disk every half a second or so, something like this, which is what essentially every database does because it's very expensive to just continually sync. But because of that, the performance concern becomes much more about what's happening in memory than on disk. So let's see if this actually worked. Here we have, here we may have broken Ubuntu, but here we've got a script that's happily writing out, so let's stop that. Oh no, except it thinks it restarted. Oh no, that's just died. Oh, let's just stop the other one. Let's bring these back up and see what happens. I genuinely don't know what's going to happen. So CouchDB A is going to start and wait until it boots. It should just take a moment. And then by the look of it, the CouchDB B VM itself has corrupted, which isn't great. That's very annoying. I may have broken my network infrastructure. Let's see if they magically... Hey, that one's still up. Cool. So this database, CouchDB, yes, it still exists and has an enormous number of documents in it, or a large number of documents in it. Not going to be able to work out which of these is the most recent, but there is a nanosecond of some. So this one has continued working despite this. The other database, not the other database. The other database I'm sure is fine, but the operating system itself, thinks it's broken. Let's very quickly see if I can actually get in here. So, which one is it that's not working? A. That does not look promising. Okay. So somewhat inconveniently, we didn't break everything. We did break everything. So that's not particularly helpful, but notably that CouchDB itself is still happily working, and the service continues, and the problem there becomes the fact that the computer is going to start to break if you pull the power out every 2 minutes. Although I did run this for the whole weekend, so it's annoying that it's failed now. CouchDB itself generally, though, is not perfect either. Notably, the write stuff does cause particular problems. The extra disk usage and the reduced performance you get versus other databases you might be writing to is not great. I think particularly if you're looking for a kind of similar database that writes quite a lot faster, React is a fairly good model for that. Not quite so focused on the flexibility and the reliability that you get on top of that, but otherwise bringing a fairly similar model. There's also obviously the general concerns you get with a document store more widely, so you can't join between stuff. Arbitrary queries don't work in quite the same model that SQL does, so you lose that kind of thing a bit.
Once you've got your CouchDB, what sort of virtual database layer would you run on top of it to give you normal SQL?
I wouldn't. So you can build...
Rather than trying people to reinvent the wheel.
So essentially you try and use it in a different model. So in our case, we were just looking things up by key, and only ever by key, which gives you a very simple model that works very well.
So if you want to make virtual tables and run sensible queries and things like that.
So generally you don't. If that's not a model that CouchDB or document stores generally really support. It requires a different design.
So data mining CouchDB is a no-no?
Yes. So
what you would have to do is serially pull all your data out and shove it into a reporting SQL server, and then you can...
yeah, you can do that kind of thing and then query over the top of that. In general, I suspect data mining is probably data mining is probably not something where you have a huge number of different readers that you want to be able to always get at it in quite the same sort of way. And there's probably other databases that are going to be more applicable to that. Cassandra, particularly, column-orientated stuff.
So does that mean, you have the B-tree thing there, are there not virtual indices that you build on top of it as well?
So you can build essentially indices on top, although really they're just more B-trees. They're focused around a MapReduce model running on top of this that you have to predefine. You can't do arbitrary queries on top. And it really doesn't want to let you do that. And it's not essentially the way it's intended to be used. CouchDB docs have some quite good discussion examples of how you design something with a normal SQL database versus how you can make that work in CouchDB's sort of model. But not everything translates. There are some things that you just don't want to do in CouchDB. It is not a tool for every case. It is a very interesting tool for this particular case where you want stuff to always be available. And I think that's very cool. And just very useful in a lot of interesting places. It's really nice that you can take this rickety, falling apart infrastructure, a selection of phones communicating with one another, and on top of that you can make something reliable where all the data shares stays there, and you can just write stuff and get at it from everywhere consistently and reliably, which is cool. That's a lot. I should say again, we are hiring. You should talk to me or Rick. And if you follow me on Twitter, I'll put the slides up after this and you can have a closer look through. Cool, thank you.
I don't know if there are questions to make too, but are there any more before we take on?
I think one thing I think I can think of some quite good use cases. And particularly things, in our case, for example, where we're writing, relatively infrequently we're writing locations of stock in warehouses, for example, and the goods in process perhaps runs overnight, and so there's a relatively small number of writes as stock is moved, but we want to be able to look up the location that a stock item exists in and so on. So I absolutely see why this could work quite nicely for us. But I'm a little bit concerned that there isn't a way that you can subsequently resynchronize if we felt that we had lost it. And I totally get what you're saying about it. This is a situation where it is more important to know where an item of stock is in the warehouse, for example, but ultimately we need there to be a way in the right where we can make sure that it is right, and if there is some difference between versions where we can resynchronize it. I just wonder if it's got an inbuilt mechanism for actually going through and check some of the data, which in and out of an hour's time or something would be quite intensive.
So the replication structure is essentially unbreakable in that the resulting documents you're going to have are all going to have revisions which are hashes of the documents which had the hash of the previous revision in. So if all your documents have the same revision, they are the same. And there's no way you're going to get around that unless you get like hash collisions or something, but you're more likely to get hit by asteroids.
So the rationale is that the hash.
It ends up being the hash of the previous hash of the previous hash of the previous hash, and you encode the entire history of each document. And if you go through and you check all the revisions, if they are the same, it must be the same. So I'm not aware of any way that you could break the replication so that you lost documents or that kind of. No, in general, yeah. If you're prepared to go through and check all the revisions, yeah, there's no problem.
I suppose the hash I mean, I'm thinking extensively using this at the moment, and ultimately my SQL encoded in binary logic changes, and in theory you connect and you pull back all the changes since the last master event title that you had, but in reality sometimes servers fail, and when they come back again, trying to work out which the last transaction was can be a little bit tricky.
Yeah, so
I guess the hash component is the advantage here, because you can quite easily see that last transaction was applied or wasn't applied.
yeah, so you can look at exactly which revisions you have available of a document, which revisions are on the previous one, and very easily see, okay, this revision is here and not here, or vice versa. And then, yeah, if you get conflicts, I think that's also sort of a part of that same problem. But there is an API to go and check for those, so you just hit that every night, however often. Any other questions?
Did you start off with some of the university projects?
CouchDB? I have absolutely no idea.
It feels like
It does feel like they've taken some interesting data structures and a thing and then built it on top of it. And there is a lot of stuff basically talking about how it's essentially just a fancy B plus tree manager, because all the MapReduce stuff works really well, so it does incremental MapReduces and this kind of thing, which is very cool, but it mostly does that by storing intermediate results in various places in a B plus tree. And a lot of it is along that kind of line, but I don't know. Anything else? Okay, thank you.
Thank you very much.